subject we're going to talk about is the properties of water. Properties of water, we're talking about water as a substance, not water necessarily as a molecule. We've already talked about the fact that water is a polar covalent bond that is holding the water, the atoms of water together, that is oxygen and hydrogens. And the fact that it's polar makes it form hydrogen bonds. And this influences a lot of the properties of water. In other words, how it acts as an overall substance. So we're going to go through some of these properties of water. And the first one I want to talk about, and these two, surface tension and capillary action, sort of go together. What surface tension is basically all of the molecules on the surface of water, that is where it meets the air, will have hydrogen bonds. In other words, it forms hydrogen bonds all along the surface, and in essence, this makes kind of like a surface that's a little bit harder. Some people, refer to it as like the skin on the water's surface. If you've ever done a belly flop, you kind of know what I'm talking about. That is that water will push back on you. And I always kind of think of this like a screen. If you think of a screen, every little hash mark or every little juncture where the screen parts interface, in other words, the little pieces that make the screen, are fairly weak. In other words, I could poke through the screen fairly easily in one location. But a screen as a whole is actually quite a thing. Like if you ran into a screen, let's say a screen on a sliding glass door, it might knock you back. So all together, those hydrogen bonds make quite a surface. This is why things float on the surface of water, why you can carry something really heavy on a barge, for example, because a barge is a long, flat surface where all the water junctures, that is the hydrogen bonds, will hold that barge up and carry really heavy objects. Okay, so capillary action is in a way related to this because it is also an air-water interface, but it's what's happening within a tube. So on the surface of the water, over here we're showing you all the hydrogen bonds forming, so you have that along here as well. But what we're talking about is what's going to happen within the tube there. Now this has to do with adhesion and cohesion, which are two properties of water, not just water, but other substances as well. But we're going to be talking about it in terms of water. What capillary action literally is the movement of water up a tube. And I have up in quotes because it doesn't have to be up. It just needs to be through a tubular type area, but it also doesn't have to be a tube. It can be just through, say, the spaces in a rock or in a root channel or something like that. So adhesion is the ability of water molecules to be attracted to something else. Or adhesion is just the ability of any substance to be attracted to another substance. So what's going to happen first is that water molecules on the surface of the water will be attracted to the sides of the tube. And when that happens, cohesion, which is the attraction of water molecules for each other, will cause the water molecules from down below to be pulled up with it. So what literally will happen is this attraction property will keep moving the water up the tube and pulling water with it until the weight of the water column in that tube, this weight of this amount of water, is so heavy that the adhesive forces are outweighed. Or another way to think about it is that the pressure of the air downward on it is so much that it's keeping it from moving up. Okay, so it's going to move up a tube. Now, as you might imagine, or maybe as you intuitively know, the smaller the tube, the faster it will go, and also the further it will go. So, like when you go to the doctor's office and they have that little tiny tube, and they prick your finger, and then, like it will just be sucked up the tube very, very quickly. Whereas if you have a very fat tube, it may only move up just a little bit. And in fact, on the edge of the beaker, you might actually see it going up on the edges, but not pulling, the water up particularly far. All right, now capillary action is the way that water moves through cracks. They can move up root channels. It helps with the movement of water through a plant, like the vessels of a plant, basically keeping that water in the vessels overnight, for example. And so capillary action ends up being a fairly important thing in biology. And in lab, when we put a cover slip on a slide, the water will spread out underneath that cover slip, and this is also a type of capillary action. Okay, the third thing that we're going to talk about is the moderation of temperature by water. Water, because of all of these hydrogen bonds, takes a fairly long time to heat up. In other words, if I were to make these molecules move, I would have to move them fast enough to break this hydrogen bond, right? So in order to get them moving, I would have to have a fair amount of heat energy. Now in liquid water, there is always some breaking of those hydrogen bonds and some reforming of those hydrogen bonds on a regular basis. This is what happens at room temperature. So in order to break those hydrogen bonds, though, from the surface, because remember up here, they are happening because of surface tension. There's hydrogen bonds all along the surface. I would have to break hydrogen bonds enough to break off into the atmosphere to change states of matter. Now it turns out in order for a water to cool down a lot, you actually need to evaporate a water molecule from the surface. In other words, I take the fastest ones out, leaving the slower ones behind, which means that makes the substance cooler. Also, it takes a while to make them stop moving. In other words, to break the surface, to get the faster ones out. And that is also related to the hydrogen bonding. So basically, hydrogen bonding is going to make it hard to start the molecules moving. It makes it hard to start them. And then once they're moving in terms of breaking the surface and getting rid of the really fast ones and therefore cooling down the substance, it also is related to the hydrogen bonding on the surface, okay? So this is moderating the temperature. If you're near water, things tend to be of a more even temperature. And this is the thing that is the type of energy that is the movement of molecules is called kinetic energy. We also call that heat. This is giving us a value called a calorie, also known as specific heat, that we measure most energy that we get from things like food, for example, and from other chemical systems. That's called the specific heat of a substance. Water has a very high specific heat, but specific heat is defined by water. So it's the amount of energy it takes to raise 1 gram of water 1 degree centigrade. Also, I want to just point out here the difference between temperature and heat. Temperature is the measure of the heat energy of something. In other words, it's like what the average heat energy of a substance is. So size really doesn't matter there. Whereas the total heat is all of the kinetic energy within a substance. So let's say if I'm looking at a lake here versus a bird. A bird may in fact have a higher temperature, that is, say for example like 35 degrees C. That might be kind of high, but anyway, something around there for a bird, whereas the lake water might only be, say, 20 degrees C, but because the lake is so much larger, it would have a higher total amount of heat. So I just wanted to talk about that a little bit. Now the fourth thing that we're going to talk about is evaporative cooling. So we've already sort of mentioned that. That is that in order to change states of matter, I have to break those bonds in the surface to take off the fastest one, leaving the cooler ones behind. So that's why, like, even in a in a room, if I had a beaker and I left a beaker there, that water would evaporate, and the beaker water would be somewhat cooler because of that. And that's also why pools are generally a little cooler and so forth, because they're losing molecules. Now, the water will evaporate. Let's say, for example, even in an air-conditioned room, and I had an open beaker, that water would evaporate eventually. So where does that heat energy come from? It comes from perhaps the water below, or it can come from the outside environment, either the air, the beaker, the table that is sitting on, whatever, or in the outside environment, outdoors. It might be something like sunlight that would be giving the heat energy. But in regards to that, even let's say, for example, when you take a shower, that water evaporating is going to take some heat energy from your skin and make you feel cooler. This is why we sweat, right? So you get a slight film of water on your skin, and it's going to cool you down. This is why dogs, cats, etc. pant, because they are evaporatively cooling off their body. That's why some animals, like desert rabbits, have very large ears, so they have an evaporative surface. So evaporative cooling is a very important biological function. Okay, the next thing we're going to talk about is frozen water. Frozen water, or water that forms all of the covalent bonds that it can, like in this picture, it can form a maximum of 4 covalent bonds. So when it does that, this takes up a lot more space than water as a liquid. So water as a liquid is actually going to be like floating around each other, not necessarily bonded to each other, and the molecules are somewhat closer. And as you cool it down, it's actually going to form what they call a lattice structure, which has more space between the molecules than it does as a liquid. And because of that, ice floats. And this is important in biology because if ice didn't float, lakes would freeze from the bottom up. And this would kill everything in the lake. And really, something like Lake Superior would never unthaw, and there wouldn't be any life in the lake whatsoever. So the fact that ice floats, this is also another thing that is related to this, is ice, or that is water, expands as it freezes, and this can break things, like say if there's water between a rock, it's going to break that rock apart. Or you might have experienced this by having a water bottle in your freezer. It might have expanded. This is actually why in a water bottle they usually make like a little divot in the bottom of it, because if it expands, then it's not going to break it open. All right. So in the other thing that we want to talk about is that we have water as a solvent. Okay, so water, generally speaking, is considered by some people a universal solvent. It's not actually, universal meaning that it could dissolve anything, but it does dissolve a lot of things, including ionic substances that are normally pretty resistant to being broken down. For example, if I put salt in a pan of water and I boiled the water out, what would be left is the salt, and it's really hard to get it to change states of matter. But in water, because of the polar nature of water, it can pull those ionic bonds or disassociate those ions from each other and surround them, and because of that, it can dissolve this ionic substance. So this is why water is a very important solvent for solutes like sodium chloride, for example. Anything that is charged, ionic, and or polar can dissolve easily in water. The things that cannot dissolve easily would be something that are non-polar. And those things are what we call hydrophobic. Things that are polar or ionic are hydrophilic. That means that they do dissolve in water. All right? So the next thing, or the last thing that we're going to talk about, is pH. If I can get it on here. All right, so here we have 2 water molecules, and when the water molecules disassociate from each other, they form hydroxide, OH, and what they call hydronium. It's also easy. This takes two water molecules. It's another way to think about it is H2O would become H plus and OH negative, which this is more official, but it's kind of easy to think of this as being just H plus. And the reason why I'm saying that is because this influences pH. pH is the, oh, I'm having trouble. Okay. pH is the negative log of the hydrogen ions in solution. And what that means is if I have a substance that is adding hydrogen to a solution, I'm going to have more hydrogen ions. And because it's a negative logarithmic function, that would make it on the lower end of the scale. So this is the highest hydrogen ions in concentration. That is, the numbers are small. And this is the lowest hydrogen ions in concentration. Now, if you have high H plus, you generally speaking would have a lower OH. That is not in pure water. In pure water, it's going to be equal amount. That is, they're going to break apart and be equal. That is why it's neutral. But in the if you have something like hydrochloric acid, for example, and it will dissociate and become add H's to solution, you're going to be more acidic. And if you have something that is adding OHs to solution, you're going to be more basic. So that is going down on this scale.